Welcome to the course on modern digital communication techniques. So, till now we have discussed source coding, and we have seen how the signals which could be analog could be converted to digital sequence, and once we have the digital sequence, then we can do different kinds of encoding scheme, and one of the objectives would be to reduce the number of bits that could be used to represent the source. So, now you can carry on further and discuss many more details of source coding. There is a huge amount of literature available on source coding, both on analog as well as digital, and there are different characteristics based source coding schemes which we will not cover in this particular course because of the time constraint and because we have to also cover other things. Our main interest was to show you or to make you aware of the things associated with source coding so that you can understand its importance with respect to communication system design. So, here onwards any further advanced things you should be able to follow based on whatever platform we have created in this particular course in the previous lectures. So, now now is the time that we have to get into design of communication systems. So, we are still preparing for seeing a complete communication system, and at this point we would like to ask the question that so we are basically trying to communicate so when we would like to write down this word that we would like to communicate, then the question that we would like to raise is what you would communicate, right, is the basic question. So, given our previous understanding, we can take a typical example, like let us take an analogy instead of directly getting into the details of communication theory. If we think communication is like sending of information, that is what we have discussed before. So, we can compare similar to a transport system which transports things from one place to another, right. So, if we take a few example of things that gets transported. So, we want to transport things to be transported from one end to another end. So, we have to design a transportation system. So, that is like pure hardware things and pure big bulk things, but it is somewhat analogous to communication. So, let us see what it is and how does it sound a bell towards the design of communication systems, or the basic questions that one should ask. So, when we are transporting things, let us say you could ask what things. So, question could be what are the things, right, that you should generally ask, because accordingly your solution is going to depend on that. So, suppose we are saying that we want to transport logs of woods, that could be one situation. We could say that we want to transport people, that could be another situation. We say that we want to transport let us say fruits, then someone could say that we could transport let us say some things made of steel, right. This is a few different things, and then you say so what if you are asking this question. So, the next important question that we should ask towards designing a solution is that this particular thing which you have identified, which could be varied, transport across what. Let us say we are talking about people. So, to be transported across a particular, we would ask the geography, right. If we say geography, we could say that it is transported over land, and then we are seeking the solution. We said, well, you can go for cars. Okay. The next question could be, well, if you are transporting people, how many people? So, your answer could be many people, it is still land, your solution could be a bus, right. Then we could move and say that, well, we now want to transport things over land. So, we could think of a truck, right. We could think of a goods train, right, and then we could think of things which are perishable, right, and over large distance. Then we could think of airplanes, right. We could think of logs of wood, and then we find that there is a river which is connecting two lands where between which it should flow, we could say that let them simply float, right. Now, if we look at this, there are certain hidden things that we are discussing behind this scenario that we have taken at. Although it may appear not directly connected to communications, but there are certain insights which you can draw from this. Certain insights, like we are trying to characterize the things based on these descriptions, and we have seen that if we think of transported across a particular geography, we are trying to characterize the link, or we are basically characterizing this as the channel, right. So, and here is the source, right, what is to be transported. The solutions would depend upon an understanding of the source, or what is to be transmitted, and or what is to be communicated or transported, and over which it has to be communicated, right. So, with this we are trying to draw an analogy that you are seeing that these solutions are customized, or in some cases you could also use the word optimized to these situations, right. So, for instance, when we talk about this perishable goods, this particular case, over long distance, we are saying that we need to transfer things, not people. So, that hints that well, you do not need seats. So, you could stack them up, and when you say perishable, you mean to say that there is a time constraint. So, there is a delay, and if you look at these solutions they involve a significant amount of time when they will transport across large distance. So, you think of as a different solution. You could say that why this solution was not used over here. The answer is very, very simple, that if I am going to use airplanes for transporting people across shorter distances, it would be very costly affair, and in some cases, let us say where the distance is 50 kilometers or 100 kilometers, it might turn out that it is in fact worse than using a car. So, what I am trying to hint at is that you need to understand what is to be sent, right, and you also need to understand over what things need to be sent. So, these are the two important things that we need to understand before we think of solutions. So, when you think of solutions, then comes the design of these things, and as well as design of the whole system. So, when we say this, not only the bus communication system is also involved in this. So, we will slowly delve into that. So, now if we are asking a question related to communications, right. So, if you are asking the questions relating to communication, again I would like to ask what is to be communicated, similar thing, what is to be communicated, communicate what, right. So, well, you can say information, that is a pretty right answer, but then how do we say that, well, what do you mean by information? That is a important question, and then we would have to go back to how things were handled years back. So, earlier, or let us say we take a direct example and we say that suppose I am seeing a light source, a light, and I say I want to convey the information about this particular source. So, let us say it has a particular color. Once that information is sent, it is sent forever, right. Now, how important is it to send information regarding this light source? The answer could be that this is important if there is change of content in that source. For example, I could say that the light or the source that we are seeing from far changes between two colors, let us say red and green, right. So, then it could make sense to send across to the other side that what is the color of the source, right. So, what I am trying to hint at and what we discussed earlier is that if there is a chance or there is a probability that we are measuring something. So, that means of course, there is a measurable, right, that means you can measure it by some mechanism, and there is a probability associated or a chance of change. If this is available, then there makes sense to communicate, right. And generally we can say that there are signals which have these kind of properties. So, they are measurable and they do change and there is a chance of changing. So, if it does not change with time, then there is hardly a point in sending some information about it. So, over a very large amount of time, the amount of information you send is negligibly small. This is something that we should be thinking in that particular direction. And when we think in this direction, we say that, well, we have certain signals, right, which are not constant and we have to send this across. So, we have got part of the initial answer, that what we have to send. So, basically the things that we are going to be talking about is going to send information in the form of signals, right. So, then as we did here, our basic question would be that we have to characterize these signals, right. So, without characterizing the signal, we will not be able to send it across a particular geography or a particular channel. That means, whether there is a delay constraint, whether do they have a particular structure, like with people, I mean definitely you need the carrier to have seats, right. Whether if it is like things, they could be stacked up in boxes, right. And then you could ask for how many such boxes could fit in, or how many such chairs could be arranged, so that so many people could be transported, right. So, the questions or the solutions would depend on characterization of this. So, what we are trying to say is that we need to characterize signals, right. And now, if we think of this as the system or the channel, so we need to characterize signals and I would say channels. Generally, this is referred to as systems. The reason is we put something input into this and we get something out of this, right. We send a certain signal into the channel, we get a certain signal out. We send people into this system and it produces people at a different place, right. We put things into it, after a certain time they get delivered and there could be certain changes to it. So, when we think of communication system, we need to characterize signals and we need to characterize systems, so that we can design a communication system. Without being able to characterize it well, a proper solution is not feasible for these things. So, when we look at or when we ask the particular question of characterizing signals and systems, we could ask the question that how could you characterize, how would you characterize signals, let us say, and there could be systems as well, right. So, there are different ways of doing it, and you could say that, well, when I look into a signal, I could say that I could characterize the signals based on whether they are deterministic or versus whether they are random, right. We will slowly get into see what do you mean by random. We have of course seen something. So, for random we can say that you cannot predict a priori what will be the outcome in the next trial, right, or what will be the value of the random variable in the next instant of time if it is a stochastic process, or in the next experimental event. So, it could be deterministic. Deterministics are the ones which are completely described by certain expressions given an initial condition. So, if you are given an initial condition and you have the relationships to exactly determine what is going to happen at a certain duration of time. So, these are deterministic. You can characterize signals based on these things. So, that is one way of doing it. You could say that, well, I could like to characterize signals as being continuous versus discrete, right. We had seen examples of continuous and we had seen discrete, right. It takes discrete values. You could say I could characterize signals based on band pass versus low pass, and this is what we are going to see very soon. You could say I would like to characterize based on whether their energy signals finite energy versus whether there is finite power, and so on and so forth. You could go on characterizing them. Now, so what if you characterize these, how does it help us in designing communication systems? So, well, what we are going to do is we would like to represent the signals within a certain framework or within a certain structure, so that we can use that particular structure in finding out the interaction the signals have with systems, so that we can calculate the output when the signals get launched into the system. And when we get the output, then we can see what kind of difference the signal has from the original form, and our job would be to reconstruct the signal back to its original form. So, based on this, we would like to analyze these particular signals that we are going to encounter in our day to day communication experience. So, before we move on to describe the actual communication system, we would like to just state a few specific signals which are very important and which may appear at certain points during the analysis of our communication system. So, one is the continuous time step function. There could be various definitions, but this is the definition that we will follow by, which will be defined as u of t is equal to 1 for t greater than 0 and equals to 0 for t which is greater than or equal to 0, and it is discontinuous at 0. So, that means you do not know what is the value. So, at 0 it is 0, just at greater than 0 it is 1. So, this is the unit step function if this is 0 and this is the time axis, right. Okay. And then there is another important function, which is the delta function. So, if you have the delta function is defined in terms of the unit step function as the integral of minus infinity to t u of we would define delta function in a way that u of t is equal to minus infinity to t delta tau d tau. Now, how do we get this? To look at this, I would like you to recall the relationship of the discrete time functions, which are much easier to visualize. So, if this is the unit step function, the delta function would be a difference of the unit step function drawn over here and the unit step function drawn in this line. So, that the difference would result in this delta function, right. And you could represent the delta of n is equal to u of n minus u of n minus 1, or you could say that u of n is equal to delta n plus u of n minus 1, which you could write as delta n. So, basically I could write delta n plus u of n minus 1, which is equal to delta n, again the recursive definition, delta n minus 1 plus u of n minus 2, and so on, which you could define in a recursive manner. U of n is equal to summation of m equals to minus infinity to n delta n. So, this gives a hint towards this kind of relationship, and you would also have delta t is equal to the derivative of u of t, right. So, these are some important relationships which we would just like to revise, and if we see that how you could get to this, you can make an approximation of u of t. So, we would rather draw it here. So, you can think of an approximation of u of t by this function, which is t, and this value is 1, let us say there is some continuity over a period delta, and then it takes this value, right. So, if you take the derivative of this particular function from 0 to delta, there is a constant slope, and that slope is basically 1 upon delta. This is 1 upon delta. So, this value you are going to get 1 upon delta, and the rest of it is 0, right. So, you are going to get this constant slope of 1 upon delta. So, if you take the area of this with limit delta tends to 0, you are going to get a value of 1 upon delta multiplied by delta. So, that means the area has been restricted to 1, and we could say that. So, at this point we could write d dt of u delta t evaluated at t between 0 to t equals to delta. What you are going to get is 1 upon delta in this whole period, and we are basically approximating. This is what we are writing as u delta of t. So, in other words, we have written that u of t is equal to limit delta tends to 0 u delta of t, and we also know that this area is equal to 1 irrespective of the value of delta, and then we could write delta t as the derivative of u delta t, and this we could write the suffix delta, and then we could say delta t is the limit capital delta goes to 0 delta subcapital delta t. That means, we are going to make delta equals to 0. This becomes narrow and narrow and narrow. So, this becomes very narrow, and the height becomes very high, and this is delta delta t. So, basically delta, right. So, as delta becomes small, this becomes higher, but the total area still remains the same value of 1, right. This way you could find the relationship between delta t and u t as well, right. So, at this point we move forward, and before we proceed with a few more expressions, I would like to say that there is another important thing which we should consider. It is like when we are analyzing systems, as we have said, that we have the channel. You have seen in this picture that signals would go into the channel and they would come out, and this is what we have described before as well. So, when you have such a system which is going to be impinged by signals and you are going to get an output, then the question arises that how do you study such systems, and so that you can get an easy or a meaningful representation. So, generally these systems are studied in terms of their eigenfunctions, right. Generally exponentials are a set of eigenfunctions for systems, and the advantage of doing so is that if you launch an exponential into the system, what you are likely to get of a system whose eigenfunctions are exponential is again another exponential with some coefficient, and the coefficient would be the eigenvalue. So, what we are trying to say is that you are launching an exponential into the system, you are getting an exponential out, and what has changed is the coefficient of this particular exponential. So, that means your study could be restricted to the coefficients of this exponential rather than the exponential itself. So, with that motivation, we would like to deal with the Fourier analysis, because when you do Fourier analysis, you are dealing with the representation of signals or systems in terms of exponentials and their coefficients. So, through that we are going to study such systems. So, let us revisit or use the definitions. X of t through the Fourier relationships is equal to 1 upon 2 pi minus infinity to infinity x of omega e to the power of j omega t d omega, where this is the time domain signal, this is the angular frequency domain signal, and x omega is the Fourier transform of x of t, right, and x of t is the inverse Fourier transform of x omega. Sometimes this is called the synthesis equation and the reverse is called the analysis equation. X of omega is equal to minus infinity to infinity x of t e to the power of minus j omega t dt, and in terms of continuous frequency f, you could write this as x of t is equal to integral minus infinity to infinity e to the power of j 2 pi f t dt, and here also we have x of f is equal to minus infinity to infinity. Here I made a mistake, here there should be x of f, and here it should be x of t e to the power of minus j 2 pi f t dt. X of f, yeah, same thing over here, right. So, with this, and of course, the relationship omega equals to 2 pi f. So, with these relationships we should be able to study the communication systems. So, moving ahead further, we would like to see that if x of omega is equal to delta of omega minus omega naught, because this is another special function. As we said that before we get into the study of communication systems, we will revise or tell you a few of the important functions which will appear again and again. So, that let us have these expressions handy with us, which we will be referring to whenever necessary. So, we define the important function delta, which you have just described, and we would like to see that in the frequency domain it is the delta function. So, what is x of t is the question, right. So, x of t is equal to, going by the definition, 1 upon 2 pi minus infinity to infinity x of omega. So, we write delta omega minus omega naught e to the power of j omega t d omega, and because it is the delta function, the job of the delta function is to collapse this entire function at omega 0. So, when you have at omega 0, that is the only value this function can ever take in this whole integral. So, what you are left with is e to the power of j omega 0 t upon 2 pi. So, in other words, we could say that if x omega is equal to 2 pi delta omega minus omega naught, then we could say that x of t is equal to e to the power of j omega naught t. Similarly, we could also have, if x of f is equal to delta f minus f naught, we have already said that f omega is equal to 2 pi f. So, if this is the case, then we have x of t is equal to e to the power of j 2 pi f naught t, or in other words we could say that if this is, if the x of t is e to the power of j 2 pi f naught t, then the Fourier transform of this is delta f minus f naught, and at omega naught equals to 0, if I say omega naught is equal to 0, what do we get is x of t is equal to 1. Similarly, this as well. So, as f would imply x of t is equal to 1, and what we have on the other hand is delta omega, and what we have over here is delta of f. So, of course, we have this 2 pi associated with this. So, if there is 1 on this side, we have a 2 pi associated here, right. So, these are some of the important relationships that we will be using in the future setting up of the expressions that involve signals and as well as systems, which we are going to encounter in the future lectures. Thank you.